So, hello students, welcome to CG Chemistry. Today we will be continuing the rotational spectroscopy, and where we will be discussing the energy of rotating molecules and the rotational constant, etc. So, coming to rotational spectroscopy, we know in each spectroscopic technique we need radiation, right? So, in rotational spectroscopy, we are using microwave radiation. Okay, so there are some certain condition, or all the molecule will not be active to the microwave. So there are some condition. The first one I wrote already, dipole moment should not be zero. Okay, the second one, perfect molecules are rotationally inactive. Okay, we know different spectroscopic technique, the condition of resonance and all. So the same thing is happening here also, because the rotating molecule frequency should match with the microwave radiation frequency, then only we will get a rotational spectra. The other important condition that you should remember is the dipole moment, or sometimes question may ask, right, what are the molecules which are rotationally active or rotationally inactive. So these are the two important conditions. Okay, so like ethine, ethylene, etc., these are like sp2 hybridized molecules. I have wrote here BF3. Okay, these molecules are rotationally inactive. Okay, now what a perfect molecule? Perfect molecule means they should possess same ligands, like you can see in BF3 and CH2 double bond CH2 BF3 N2 H2 etc. Same ligands, and there should not be any lone pair. Such a molecules earlier we discussed in the last video for the spherical top system. I already mentioned about the perfect molecule, like perfect tetrahedral, perfect octahedral molecule. Okay, so such type of molecule will not be rotationally active. So this rotational spectroscopy is otherwise called microwave spectroscopy, that you might be knowing. Okay, so the inactive molecule, I mean that perfect molecule will be same ligand, and there should not be any lone pair on the molecule. Okay, അപ്പോൾ lone pairs ഉണ്ടെങ്കിലും അതിൻ്റെ ligands same ആയിരിക്കും. ഓക്കെ, അപ്പം അത് നമുക്കപ്പം എക്സാമ്പിൾസ് തരുവാണെങ്കിൽ, ഇഫ് ദേ ആർ പ്രൊവൈഡിങ് സം എക്സാമ്പിൾസ് ആൻഡ് വി ആർ സപ്പോസ് ടു സെലക്ട് what are the active molecules and what are the inactive molecule, by simply noting out their whether they are perfect molecule, you can simply tell, and the dipole moment condition also, you can tell whether it is rotationally active or rotationally inactive. Okay, so this type of molecules, whatever I am writing here, these molecules are rotationally inactive. Okay, like CH triple bond CH, CH2 CH2 N2 H2 BF3 CO2. These molecules are rotationally or microwave inactive molecules. Now, what are the rotationally active molecules? Okay, so this type of questions will not be I mean not much asking in the CSIR net questions, but you should know. Okay, so active molecules are, like you see it has examples SF4, HOCl, H2S, etc. So if they are asking questions by coupling all this two, all this whatever I wrote, inactive, active, you might be knowing how to select the active and inactive molecules and separating out, right? So this is just a simple starting of microwave spectroscopy. I just want to tell you what are the molecules which are rotationally active. Okay, now we will move to the energy condition, that we know in all the spectroscopic conditions. We might be studying the energy criteria, right? The energy criteria of if it is rotational, the rotational molecule, the rotating energy, then vibrational energy, like that, translation energy. Every type of molecules is possessing energy. So the energy of the rotating molecule is given here as the equation h square divided by 8 pi square I j into j plus 1. So this equation is derived from quantum mechanics, and now time being we are not going going into the detail of deriving this equation, okay, because we don't want such things. So here J is what? J is the rotational quantum number, or it is the different energy levels. Basically J is the different energy levels here, like J can be 0, 1, 2, 3, etc. So 0 is the ground state, 0, 1 means 1, 2, 3 are the higher excited state, okay. Now you see here H, what is H? H is the Planck's constant. I is the moment of inertia, right? So the moment of inertia equation and all in the last video we discussed, it is sigma m ri square, okay, right. Other for different molecules like HCl, it will be mu r square. Mu is the reduced mass that we know, and this energy is in joules, okay. The energy that we are expressing here, h square by 8 pi square j into j plus 1 in joule. Now suppose if they are asking the energy in centimeter inverse, okay, so sometimes you some questions might be coming in centimeter inverse. How to convert this joule to centimeter inverse? You have to divide this energy by hc, that is Planck constant multiplied by velocity of light. If you divide this energy in joules by hc, you will get the energy in terms of centimeter inverse, okay. So what is h? H value also you should know. It was like 6.626 into 10 raised to minus 34 joule second. Joule second is the unit of Planck's constant, right? I will write here into 10 raised to minus 34 joule second. Now you see here part we will discuss, and can see that velocity of light 3 into 10 raised to 8 meter per second, or it is 3 into 10 raised to 10 centimeter per second. Because we want to convert it in centimeter inverse, I am writing it in centimeter, okay. So in between some problems happened in the video, so that's why I am starting just from the, not from the beginning. We will just look that converting the joule to centimeter inverse, okay. So this is the equation. E is h square by 8 pi square I j into j plus 1, okay, that is in joules. Now we want to convert it in centimeter inverse. So in converting centimeter inverse, we have to divide the equation by hc. So E by hc, right? If you divide this equation, that is the energy equation in joules, by hc, you will get the energy in centimeter inverse. So let's divide h square by 8 pi square ic by hc j into j plus 1. Okay. Now what happens? You can see that h value, you know, 6.626 into 10 raised to minus 34 joule second, and the velocity of light c is 3 into 10 raised to 10 centimeter per second, okay. So you see h will cut, so h by 8 pi square I c j into j plus 1, h by 8 pi square I c j into j plus 1 will be the new equation, where we can write it as bj into j plus 1, where b is h by 8 pi square ic, that I am taking as a constant, okay. So this constant, that h by 8 pi square ic, is the rotational constant. And you see that j, I mean joule was the in initial energy, right? Initial energy. How to convert centimeter inverse? Joule by joule second, centimeter per second, centimeter inverse. You see joule was the initial energy divided by h, Planck's constant, joule second, into meter per second. So okay, I think you understood this idea. So next, the energy is bj into j plus 1. So now we are going to see the rotational spectra, how it will look like, okay, where j is the different energy levels. Now let us see, when j is equal to 0, what is the energy? When j is 0, you substitute, it will be 0, right? Energy will be 0. Now when j is equal to 1, what is the equation? 1 plus 1, 2, 2b. Now j equal to 3, it is 3 plus what will be 3 plus 1, 4, 4 into 3, 12. Right, 4 plus 3, what is happening? Yeah, it is not 3, it is 2. J equal to 2, 2 plus 1, 3, 3 into 2, 6, 6b. Next, we can write, you write all the energy levels. Next will be J equal to, J equal to 3. So that is 3 plus 1, 4, 4 into 3, 12b. 4, 4 plus 1, 5 into 4, 20b, etc. Right? Now let us see the difference between each level. It is 2b, then next is 4b, next one is 8b, then 10b, right? I mean after the 20 it will be 10b. Okay, so 2b, 4b, 6b, 8b, 10b, etc. It will be higher energy, it will be continuing. So now we will look only up to this time being. Okay, so how a rotational spectrum will look like? The ground state will be 0, next higher excited state line will be 2b, right? Next one 4b, next one 6b, next one will be 8b. It is not that 2b, 6b, 12b, that is the energy. Okay, rotational lines will be coming in with 2b, 4b, 6. What is the energy gap? It is 2b, 4b gap is 2b, then 4b, 6b gap is 2b again, 6b, 8b gap is again 2b, and 8b, 10b gap is again 2b. So the gap between the two rotational lines are 2b. That you should remember, because so many questions will be coming. They may ask questions like they are given term 2 lines, in between the line you have to find out. Like that such a questions can ask. Now let us numerically find out what is the energy difference between two rotational levels. Okay, for that I am writing this one: J equal to 0, J equal to 1, J equal to 2, etc. I have to find out delta E, energy difference from J to J plus 1. Okay, so here ground state is J equal to 0 to J equal to 1. The equation is E is Bj into J plus 1. So now we have to substitute this J plus 1 to J. So delta E is E final minus Ei. So J plus 1 is the final. So here J is 0, J plus 1 means that is the first excited state. So E final minus Ei, right? How you will give E final minus Ei? J plus 1 is the final. So you substitute J plus 1 in the J value in Bj into J plus 1. So substituting, you will get it is Bj B into J plus 1, J plus 1 plus 1, that is J plus 2 minus Bj into J plus 1. Bj plus 1, B into J plus 1, B into J plus 1 common. You can take it out. So it is J plus 2, right? J plus 2 minus J. Now J cancels out, 2B into J plus 1. Okay, so this is the energy level difference between the two rotational spectra. Okay, so this is the energy level difference, and the problems we will be doing in the last of rotational spectroscopy. So thank you for watching, and we will meet in the next class. Okay.